Welcome to the lecture on Biocontrol Systems. This lecture focuses on the topic Modeling of Mechanical Translational System. A mechanical translational system has three important parameters: mass M, a viscous friction coefficient represented as B, and stiffness of the spring represented as K. The input to a mechanical translational system will be a force represented as F, and the output of the system might be considered as a displacement X. As we can see in the slide, the mass element M is considered, the force F is provided as input, and because of the force, there is a resultant displacement represented as X. This particular figure, the mass element is fixed to one end and it is free in the other end. There is a possibility of the mass element be available unfixed, where a force will be applied and there might be a movement or the displacement X. Similarly, if you see this figure, the viscous friction coefficient B is not fixed to an end. So a force is applied, and because of that, there will be a resultant displacement which is considered to be x1 minus x2 or x2 minus x1. When we want to convert a time domain equation into a frequency domain equation, we would parallelly consider Laplace transformation. Let us start with an example. Let us consider we have a mass element M fixed to one end, and a force is applied to that mass element, and because of that force, a displacement X is considered as the output. Well, while you are writing the force equation, force is equal to mass into acceleration, where the representation of mass is M and the representation of acceleration is a second order derivative of the displacement x of t, which is d squared x of t by dt squared. If we want to write the same equation in terms of velocity, then the mass element into the first order differentiation of velocity, that is d by dt of v of t, can be considered. Similarly, we can write the force equations for the viscous friction coefficient. In case 1, the viscous friction coefficient is considered to be fixed to one end. A force is applied, and because of that force, a displacement x of t is considered to be the output. The force equation F can be written as F is equal to B, representation of the viscous friction coefficient, into dx of t by dt, or in terms of velocity, B into v of t. Let us consider case 2, where the viscous friction coefficient is not fixed to another end. So the force is applied might result in a differential displacement. It might be dx1 minus x2 by dt, which is represented here. So force is equal to B into d by dt into x1 of t minus x2 of t, if x1 is considered as the primary displacement. Otherwise, if you are considering x2 as the primary displacement, then the equation can be reassembled as F is equal to B into the first order differentiation considering x2 as the primary displacement. So x2 of t minus x1 of t. In the same way, we can also write force equations considering the spring constant. We have again two cases. The case 1 considers a spring to be fixed to one end and a force is applied. So the displacement x of t is happening. The force equation can be written as F is equal to k into x of t. Let us consider case 2 where it is not fixed, it's free at both ends. The force equation F can be written as F is equal to k into x1 minus x2 if x1 is considered as the primary displacement. Similarly, the force equation F can be written as k into x2 of t minus x1 of t if x2 is considered to be the primary displacement. Hope you enjoyed this lecture. We will see some example problems in the next lecture. Thank you.